All right, shall we? I'll go ahead and kick us off. This is Tim Murphy, and welcome everyone to the June meeting of the Science Engineering Council. We're here second Wednesday of the month, still doing this on Zoom until we can resume our in-person meetings. So thanks for joining. I want to also welcome now our new and renewing members. We have two renewing members, David Flattery and Craig Lewis. I'm not sure if either of you gentlemen are here today. If you can, just acknowledge. Otherwise, welcome back as members. And board members, myself, Tim Murphy, we got Yvonne DeGraw, Bill Theringer, Steve Skopatz, Mary Howe Grant, Bob Lilly, and Cheryl Ebner are on the line here. And again, thanks to everybody for their donations for these meetings. That's very helpful in managing our administrative expenses. So I really appreciate that. And it also goes toward supporting our Science Fair Awards. That's kind of all the announcements we have. We've got our sponsors showing on the screen there. A quick shout out to Community West Bank, Minoa Enterprises, and, as well as Bengal Engineering and Toyon. Those our sponsors are also critical to our ongoing programs here. So with that, I'll go ahead, turn it over to Yvonne to introduce today's speaker and talk a bit about upcoming meetings.
Great, thank you, Tim. Hello, everyone. We have a full slate of upcoming talks scheduled through August, and hopefully we'll return to in-person luncheons sometime soon, but for now we're on Zoom. Our next meeting will be July 13th with Dr. Galen Moody from UCSB's Electrical and Computer Engineering Department. He'll speak on quantum computing and quantum photonics, and we'll have more information out on that soon. And on August 10th, Dr. Christopher Richardson from UCSB's Biology Department will be speaking on DNA damage repair. Today, we're very happy to have Dr. Rachel Street from the Las Cumbres Observatory speaking to us on hunting isolated black holes with microlensing. Dr. Street joined the Las Cumbres Observatory as a postdoctoral scholar in 2007 and has since become a staff scientist. She specializes in the detection and characterization of exoplanets, initially as a founding member of the Super WASP Transit Survey, for which she received the RAS Group Achievement Award. At Las Cumbres Observatory, she began to study exoplanets via the transient phenomenon of microlensing and now leads the microlensing group there. In the course of her research, she developed the automated target and observation management software to make and manage observations through the LCO network. This motivated her to lead the Tomcat project and the community development program, which make these powerful observing tools available to the community. Dr. Street was elected as co-chair of the Transients and Variable Stars Science Collaboration in 2017. So we're happy to have her speaking today. You can post questions to the Zoom chat, or you can unmute yourself to ask them after Dr. Street's talk. So Dr. Street, go ahead. I'll stop sharing here.
Hello, and thank you very much for that introduction. I will just set my screen up for sharing here. And I need to share that screen with sound. And hopefully you're looking at my slides.
Yes.
Somebody could nod, that's great. Thank you very much.
Looks great.
Well, thank you very much again for the invitation to speak to you today. I'd like to share with you some of the fascinating research that I've been fortunate enough to get involved with, searching for arguably some of the most elusive objects in the universe. But before I go any further, allow me to give all credit to the lead of the program, Kailash Sahu from the Space Telescope Science Institute, and the rest of his multinational team. This was very much a team effort and involved observers around the world. And I'll be introducing the work by our team and many others throughout this talk. So black holes have long captured the imagination of scientists and the public alike. These are regions where gravity distorts space-time so strongly that even light cannot be observed from them. The idea of so-called dark stars grew out as a logical consequence of gravitational theory, and their existence was predicted as far back as the 18th century by John Michell and Pierre-Simon Laplace. Being the most extreme naturally occurring circumstances predicted by the theory and subsequently by general relativity, The detection of black holes is one of the signature tests of those theories. So, based on that theory, black holes are supposed to be extremely simple objects. All mass is crushed into a central singularity. And around that radius is a radius beyond which the velocity needed to escape the gravitational pull exceeds the speed of light. It's often referred to as an event horizon, though it's more of a characteristic radius than any kind of physical boundary. In reality, black holes have just three physical properties. They have mass, they can have electric charge, and they can have angular momentum. But since they're not self-luminous, they are notoriously hard to detect. But so what? Black holes might be an intellectual curiosity, but what do they actually tell us about the universe? Well, it turns out that these enigmatic objects could be quite revealing. The first thing to understand is that there are several different categories of black hole, and they're predicted to form in distinctly different circumstances. So the theory is that if we measure the population of black holes that we see in nature, then we can shed light on the formation theories of many other categories of objects. So perhaps the most familiar type is the stellar mass black hole. These are thought to form as the endpoint of the life cycle of a massive star. Stars are thought to form by the gravitational fragmentation of clouds of gas and dust, and as a result, they can form in a wide range of masses, anything from 1/10 of the mass of the sun up to over 100 times that size. So most massive stars are quite quick to burn through their available nuclear fuel in the nuclear fusion processes. And once those processes start to falter, the star can no longer generate enough energy and heat to counteract its own self-gravity caused by its large mass. And as a result, it collapses in on itself, forcing the matter at the center of the star into exotic degenerate states. At that point, stars tend to explode in a rather exciting range of supernovae, but an ultra-dense core can be left behind. And if the total mass of that core exceeds about 3 or 4 solar masses, then no state of matter is dense enough to resist the inward pressure of gravity, and the material is forced into a singularity. But we do know that much, much larger black holes have been observed that are quite different in character, with masses that are billions of times that of the sun. This category includes the supermassive black holes observed in the centers of galaxies, and most strikingly by the Event Horizon Telescope. Sorry, can you hear me okay?
Yes, we can hear you fine. Thank you.
Great. So the Event Horizon Telescope recently released this image of the black hole in Sagittarius A star at the center of the Milky Way. And I'd like to give a quick shout out to a member of this team that has a local connection. Graduate student Joseph Farah of UCSB and of Les Cumbres is a member of that team. So how could these objects have formed? How could they be remnants of stars that lived and died very early on in the universe? Have they simply been accumulating mass ever since? Well, there's a problem with that theory, as it was discovered because supermassive black holes have a nice feature that they are in fact detectable. Black holes famously gobble up all of the material that actually approaches them beyond their radius. But in general, the material doesn't fall directly into the hole. Instead, it kind of spirals in, rather like water draining down a sink. In the process, I'll just run that video again very quickly. In the process, the material forms an accretion disk around the black hole as it spirals in, and the closer it gets to the event horizon, the hotter that material becomes. And so it radiates in increasingly short wavelengths of light, right up to gamma and X-rays. So since this radiation is emitted from the material of the surrounding disk, it's outside the event horizon, and that can therefore just about escape the gravitational pull of the black hole, which allows us to detect it. So naturally, there have been surveys for such objects at extreme wavelengths, and they've detected supermassive black holes in the centers of active galaxies. at extremely high redshifts, meaning that these objects have already existed less than 1 billion years after the Big Bang. But that's an issue because if supermassive black holes formed, they started out as stellar mass black holes that simply grew by accumulating material, then that process would take roughly the age of the universe for them to reach that size. So where did they come from? They must have formed by a different mechanism. And so for that reason, we consider these objects to be in a different category from stellar mass black holes. But potentially, black holes could have formed earlier still. There's a concept of primordial black holes, which was proposed by Zeldovich and Novikov in 1966. This was because conditions in the very, very early universe, where everything was in a much smaller, denser state, there could be localized regions of extreme high density, which, according to their calculations, could potentially collapse to form black holes directly. And since this category of black holes doesn't form stars at all, their masses could span an enormously large range, anything from as tiny as 10 to the minus 8th of a kilogram, right up to thousands of times the mass of the sun. So primordial black holes have been considered as one potential candidate to explain the existence of dark matter. So detecting those has been a big open question in cosmology. So for our purposes, the key takeaway here is simply that black holes are not all alike. Various different theories predict that they can form by quite different mechanisms. And so this is the reason why researchers from several different branches of astrophysics are very keen to understand what is the population of black holes out there in the universe. Since various different mechanisms can predict the production of black holes, each of them has quite a wide range of masses in each case. So if we can find a significant sample of black holes and measure their masses, then the distribution of the mass of the population should give us some constraints on their origin and their evolution. Which all sounds good, but it's a simple matter of implementation then. So clearly this is a huge topic and it touches on many branches of astrophysics. And if I covered all of the evidence for all 3 types of black hole, then this would be a very long talk. So instead, I really hope to give you a flavor of the context for why measuring the mass distribution of black holes is so important. And for the rest of the talk, I'm going to focus on just the stellar mass category of black holes because they're most relevant to my research. So the question is, how do we detect invisible objects? Well, there are a few telltale signatures that can give away even these most elusive of objects. We touched earlier on the possibility of detecting the signature of material in falling into the black hole just before it reaches that point of no return. And the same principle can be applied to stellar mass black holes if they happen to form in a binary star. If the partner star of the binary is in a close enough orbit with the black hole, then material from the star can be torn away and spirals into the black hole. On its way in, it forms a smaller version of the accretion disk as we saw before, and friction increases as the material gets closer in, causing the material to heat up and radiate in X-rays. This kind of binary star is therefore known unimaginatively as a black hole X-ray binary, and they are noted for their outbursts, where they can suddenly start to radiate very, very brightly for a period of time, sometimes weeks, before dropping back down into a quiescent state. We think this happens because the material infalling is kind of lumpy, although the accretion physics is quite complicated. So that's a bit of a generalization. So that's the first way that we can find stellar mass black holes, provided that they form in binary stars. If both components of a binary star have evolved to become black holes, then we've recently acquired a new way to detect them, thanks to the advent of gravitational wave detectors such as LIGO. If the black holes are in a very close orbit, then they can lose gradually angular momentum and spiral into one another, thanks to an ergosphere of material just outside their individual event horizons. And eventually that can lead to the merger of the two holes into a single larger black hole. And that process causes a measurable cyclical distortion in spacetimes, which is detectable now as a gravitational wave signature. Now, here is a representation of the signature of a real-world detection from LIGO presented as an audio wave. Gravitational waves can be used like this to detect black holes in the binary stars. So let's hope that you can hear this. And that chirrup you could hear was the final seconds right before the two black holes merge into a single object. So in both of the gravitational wave detections and the X-ray binaries, we have a way to measure the masses of the black hole involved because the black holes happen to be in binaries, so they can be measured from the dynamics. However, the presence of a companion in the binary system can substantially change the evolution of an object. So a single black hole can have quite different formation histories. And it's estimated that approximately 30% of massive stars are initially single. So black holes can become single during their transition from a massive dying star. If they originally had a close-in companion, that star can be engulfed as the dying star's atmosphere expands right before it explodes as a supernova. And even if the companion star is lucky enough to survive that process, it can still be ejected entirely when the supernova happens and cause it a natal kick and throw it out from the binary system entirely. So singleton black holes are particularly interesting because their formation will have evolved in the most isolated way and will therefore be less altered by interactions with any companion. And so they give us the most direct probe of black hole formation. So it's important to measure the population of isolated stellar mass black holes. But how do you find an isolated stellar mass black hole? Any material that it did have as an accretion disk would be quickly consumed, and there should be no optical or gravitational wave signature. Well, this is where the technique of microlensing comes in. Microlensing works by looking for the signature of the gravity of the black hole on unrelated stars in the background. On the left in this movie, you can see a telescope icon that represents an observer on Earth looking towards a source star on the very right-hand side. And in the middle, you can see a representation of the black hole. Though objects in our galaxy move very slowly from the point of view of an observer on Earth, they do move. And that means that eventually you do get to chance alignments where one star passes directly in front of another. And since general relativity tells us that the gravity of the foreground object bends spacetime around it, the path of the light rays from the background object are deflected around the object in the middle, creating images of the source which move in conjunction with the relative motion of the two objects. And in this sense, the foreground object is acting as a lens. Now you'll notice that I haven't mentioned what the foreground object is. It only matters that it has gravity, mass, and hence has gravity. And significantly, the only light in this situation that the observer receives comes from the background source star, not from the foreground lens. And this means that the technique is capable of detecting objects that are entirely dark, including isolated black holes. So when this phenomena occurs for stellar mass objects, the deflection of the light rays is very, very small, leading to the name of microlensing. As a result, we generally don't resolve the two images distinctly. Instead, lensing directs more of the light of the background source star to the observer than they would usually receive. That means if we monitor the brightness of that background star over a period of time, then we see it gradually get brighter as it becomes magnified when the lens approaches alignment, and then demagnified again as it moves away. But in addition to monitoring the brightness of the source star, which we call the photometric signature, we can also monitor its apparent position, or the astrometric signature, as a function of time. This animation shows the same microlensing event, but shown from the point of view of the observer on Earth looking directly towards that background source star. If we chart the apparent movement or the apparent position of the source as a function of time, you can see this apparent movement of the photocenter as caused by the passage of the lens between us. Now, this animation shows a very extreme example of the change in position of the source so that we can see it. In practice, the amplitude of that movement is extremely small. So to detect these two signatures, we can plot both the brightness of the source and its apparent position as a function of time. And to give you a sense for these measurements, these figures plot the expected signature for a 5 solar mass black hole located a couple of kiloparsecs away from the Earth, passing in front of a background source star in the center of our galaxy. A few key takeaway numbers to remember here. The first is that the characteristic event timescale is typically over 100 days, which in terms of astronomical variability is actually quite a long timescale. Sometimes black hole events can last multiple years, but the source star's brightness can be magnified by several factors, which makes it relatively easy to detect. And the peak magnification is related purely to how closely separated the lens is from the source when it gets closest alignment. Now, interestingly, the apparent movement of the source can actually be measured over a much longer period of time than the magnification of its light. But crucially, that signature is directly proportional to the mass of the lensing object. So the combination of the two measurements is particularly powerful because the brightness signature by itself suffers from several degeneracies. Because we can't usually resolve the images, the individual images of the source, the light curve of the event, which you can see in the bottom left-hand corner there, can look exactly the same for quite different physical events. In this example, I've shown two events where the lens takes different trajectories relative to the source and relative to the line of sight from Earth to the source. But we observe the same brightness signature regardless of the relative trajectory of the lens and the source. And here's another example. If we measure the angular separation on the sky between the lens and source, it's quite difficult for us to tell the difference between a relatively nearby but low mass lens compared with a more massive object, which is placed at a greater distance. So measuring the astrometric signature, that's the positional signature, at the same time as the brightness one, gives us a way to break those model degeneracies. And it provides us with information on the relative trajectory of the two objects. This means that by combining both the photometric and the astrometric signatures, it's possible to measure not just the mass of the lensing object, but also its transverse velocity. And we can start to look at the dynamics of objects that are otherwise invisible. So microlensing events can tell us a great deal, but only if we can find them. And that's not entirely trivial either. The technique quite literally depends on the chance alignment of two completely unrelated objects in the sky, and that happens about as often as you might imagine. The fact and the odds of two stars aligning precisely enough for us to observe a lensing event are actually close to 1 in a million for most parts of the sky, based on models of galactic population dynamics, such as the one you see on screen. That said, microlensing is most likely to occur in parts of the sky where they are most densely populated. So our surveys have concentrated on regions towards the galactic bulge, which you can see highlighted in red, where we can see deep into the center of the Milky Way. There we go. So a number of surveys of this region have now been in operation for about 25 years, most notably the OGLE, MOA, and KMTNet surveys. They provide a long-term monitoring of the brightnesses of all of the stars over a large area. And although they do survey the whole of the area shown in this plot, they concentrate most intensively in the central bulge area. That's right at the center of the galaxy. But until recently, they generally couldn't monitor 24/7. So they issued discovery alerts, which they sent out to the wider astronomical community and encouraged observations by other facilities. And a number of follow-up teams responded to those alerts in real time to provide complementary observations at higher frequency. And it's those observations that Les Cumbres Observatory is ideally suited for. And so my team got involved in providing the follow-up observations for these events. Now, it's important to note that the ground-based telescopes generally don't have the spatial resolution high enough to do the positional measurements of these events. So they tend to concentrate on detecting the brightness signature instead. But they have discovered a wealth of events, including many planetary systems. And typically, these surveys report around 2,000 lensing events every year. But the vast majority of those events are not caused by black holes. As you'd expect, the majority of lenses are simply stars in our galaxy that pass between us and the galactic center. Nevertheless, one of the ground-based surveys, OGLE, provides an excellent, very long baseline data set for searching for black hole events. And in 2016, Łukasz Wyzykowski searched this huge database looking for events that might be due to black hole lenses. To do that, he looked for events with the characteristic very long time scale. And the baseline of the data set allowed him to rule out alternative forms of variability from the candidates that he selected. Now, he was able to identify 59 potential candidates, and this figure shows their spatial distribution as filled dots, so the black dots on this survey image, and this shows them overlaid in an image of the galactic center region, which we call the galactic bulge. So this plot shows an example of the brightness measurement as a function of time for one of his candidate targets. The brightnesses of the source, as you can see plotted, is the black data points, and the green model represents the classic microlensing light curve with its smooth increase and decrease. But when you have a timescale of an event as long as this one, which is about 2 years, we also have to take into account the parallax signature, which causes this sinusoidal periodic waveform in the light curve. Now, although both the lens and the source are extremely distant from Earth, about halfway into the center of the galaxy, any tiny subtle change in the alignment of the observer on Earth to the lens and the source is evident in the signature from this event. And in an event this long, the waves that you can see in this light curve are caused by the movement of the Earth in its orbit around the sun. Now, Wyzykowski had to take this into account in his modeling of all of the candidate events. But the ground-based data alone were insufficient to break the degeneracies in the model that I mentioned earlier, and they couldn't measure explicitly the lens mass and distance. So instead, the most probable values for these quantities were estimated statistically from a galactic population model. And they used the inferred masses to estimate how bright the objects would have been if they were self-luminous stars. And in 13 of these cases, they inferred that they should have been able to detect the light from a self-luminous object, but they didn't. And that implies that the lensing objects were potentially black holes. But tantalizingly, that was as close as the ground-based data alone could take us. So near, but yet so far. So this was the motivation for undertaking a search for the positional signature of microlensing. But as I mentioned earlier, that positional signature is so small that it requires much higher spatial resolution imaging. And the main limiting factor on spatial resolution from the ground is the turbulence of Earth's atmosphere, which effectively causes the images of the stars to be blurred. Now, there are two ways of overcoming that and achieving a higher resolution. The first is to use adaptive optics imaging, which is available from some large ground-based telescopes. They tend to be oversubscribed and have not traditionally been used for microlensing. The other way is to fly a telescope above the Earth's atmosphere entirely, such as the Hubble Space Telescope. Now, of course, this superb facility is also oversubscribed, but in this instance, the lead of the program, Kailash Sahu, is a member of staff at the Space Telescope Science Institute, so it was a natural choice for him to conduct the study using the Hubble Space Telescope. So in 2009, Kailash Sahu and his team began to observe a program of very carefully selected microlensing events using the Wide Field Imager 3 on Hubble. And I say carefully selected because Hubble has a relatively narrow field of view, just 2.7 arc minutes across. So it's very time consuming to monitor a large area of the sky the way that the ground-based surveys do. Instead, the Hubble program relied on ground-based surveys to discover microlensing events and to send out alerts while they were still in progress. Sahu and the team then narrowed down the selection by looking for events which seemed to have the characteristics of black hole lenses, those with long timescales, and those where the modeling of the ground-based data indicated very little light from neighboring stars and a high lensing magnification. And over the course of the program so far, just 10 events have met those criteria. So after many years of very patient observing, this program finally recently announced its first strong discovery. Two papers about this particular target came out almost simultaneously in January of this year, one led by Kailash Sahu, the PI of the program, and the other from an independent team led by Casey Lam. The Sahu paper concentrates on just one of the 10 objects observed by the program and concludes that the lens must be a black hole. Meanwhile, the Lam paper analyzed the data for 5 of the events from the program in parallel, and also concluded that this particular target must be a compact object, meaning a black hole or neutron star. So let's take a look at the evidence. The target causing so much excitement goes by the very catchy name of MOA 2011 BLG 191, OGLE 2011 BLG 40462, which is a terrible name, I agree, but it's named that way because it was discovered by 2 of the ground-based surveys, both OGLE and MOA, and the MOA discovery was announced slightly before the OGLE one. So analysis of the ground-based data, which was performed in real time, fairly quickly revealed that this would be a good candidate for the HST program. It was predicted to have the long timescale characteristic of a black hole lens and relatively few neighbor stars within the resolution of the HST. So this, you can see on the screen, is the reference image taken by the Hubble Space Telescope, which shows at the center the target circled in green. And the outer 2 circles have radii of 1 and 2 arc seconds respectively. And that represents the typical best resolution that we can get from Earth without using special optics. So you can see that from Earth, there would be a number of other stars that would be blended in together with the light from this source star. But from Hubble, the degree of blending was relatively low. And so the team asked the Hubble telescope to monitor this event at infrequent intervals over the next few years. And you can visibly see the lens star fade as it gradually changes in magnification as the lensing event moves out of alignment. On the right-hand side of the screen, you can see the light curve derived from the imaging data, measured from this image sequence. And these data were used in the modeling of the event. At the same time, ground-based observatories also continued to monitor the event. As the two surveys which found the event couldn't monitor it around the clock, a team of other follow-up telescopes joined the effort to make sure that the light curve was well sampled throughout. And I should note that my own team from those Cumbres were part of that global effort, contributing data from two of our telescopes. Now, since this is real-world ground-based data, you can see that not all of the ground-based telescopes were fortunate with the weather during this event. And this shows up in the light curve as sections of data points with high scatter. Now, of course, that's something that the Hubble data is immune to. But the distinctive feature of the Hubble data is that it has such high resolution that we can use it to derive the positional measurement as well as the measurement of brightness. In this plot, the red triangles represent the measured positions of the background source star at intervals throughout the event. If the normal movement of the star had continued without the lensing event at all, then these red triangles would line up on the black line. But as you can see, the source was clearly deflected away from that line as a result of the lens passing in front of it. The position of the lens, which we can now infer from modeling those data, is represented by the purple line. And that is a wavy line, not because of the lens movement, but rather because the observer here on Earth was also moving during that event. Both Earth and the Hubble telescope were moving in orbit around the sun, and because that changes our line of sight to the source and the lens, we get this is projected onto this plot as that sinusoidal movement in the position of the lens. So when the event was analyzed, these positional measurements were modeled together with the photometric measurements of the brightness from both Hubble Space Telescope and all the ground-based data. And it's from that combination of data that we measure the parameters of this event. Unfortunately, though, the model parameters don't give us all the characteristics of the lens just yet. The combination of photometry and astrometry measures the mass of the lens, but it determines only the relative parallax between the lens and the source. That in turn depends on the distance of the source and the lens away from the Earth. But if we can measure the distance of one of either the lens or the source, then we can infer the distance to the other from the measurements that we've taken. Unfortunately, there is a way to estimate how far away the source star is, because unlike the lens, we do receive light from the source. If we break the light of any star into its component wavelengths, we can tell a great deal about its physical and chemical properties. This image shows a montage of the spectra for each star of a range of different masses. And it shows you how those spectra change as a result of the star's physical properties. The dark lines in the spectra are produced by constituents of the star's atmosphere absorbing the light at those wavelengths. And the width and the depth of those lines are very sensitive to the surface temperature and the gravity of the star. So if we get spectroscopic data of sufficiently high resolution, then it's possible to measure the properties of the source star during the lensing event. And happily, this particular event was bright enough that Bensby et al. Were able to get high resolution spectroscopy. And that showed that the source star had a temperature similar to that of the sun, but with a slightly lower surface gravity. And that suggests that it's slightly further along its evolution relative to the sun. Now, stars are quite predictable in their physical properties. The more massive they are, the hotter they are. And by comparing the measurements that we make with theoretical models of stellar evolution, we can infer the brightness of the star in an absolute scale. And we can then compare that brightness with the measured brightness from Hubble Space Telescope and use the difference between the two to estimate the distance to the source. And that then gives us the distance to the lens. So with all of these lines of evidence coming together, we can at last take a look at the physical properties of this lens. And since the two independent teams have modeled some of the data separately, I'm showing here a comparison of the results. The LAM team models two different models, each using a slightly different weighting scheme for the data to combine the ground-based and space-based data. So I've included both of those. But one important caveat to note is that the SAHU team included additional data in their analysis, which is one reason for some of the variance in the answers. And there's ongoing work between the teams to try and reconcile those results. But in the meantime, we can say two very important things about the mystery lens that's causing this event. One is that it's a massive object. All of the results indicate that it is several times the mass of the sun. And two, that it is around 1.5 kiloparsecs from Earth, which in astronomical terms is actually quite close. And that's important because we should have been able to see light from a lens that close. Most astrophysical objects that we know about produce light, and at that distance, we should have been able to see the light in our data. But we can rule that out from the data that we obtained. So that means straight away that it has to be a compact object. It has to be a star that has collapsed under its own gravity to form an ultra-dense form of degenerate matter. And that means there are three options at this point. It could be a white dwarf, a neutron star, or a black hole. Well, particle physics tells us that there is a theoretical maximum to the mass that a white dwarf could take before electron degeneracy is insufficient to support the star. And at that point, it has to collapse even further to become a neutron star. And that theoretical maximum limit is 1.2 times the mass of the sun. So we can say that the lensing object isn't a white dwarf. Neutron stars are more dense and they can reach greater masses, but there's a maximum mass for them as well. And after that, there is no force in nature that can resist the pull of gravity. And that limit is around 2.2 solar masses. Now, the mass inferred from both the SAHU model and the LAM's default weighted model is in excess of 2.2 solar masses. Even the mass from LAM's other model produces a mass right around the boundary of the neutron star limit. So it is highly likely that the lensing object isn't a neutron star either. And that really leaves only one other option. The invisible object causing the microlensing signature really has to be an isolated black hole. So I hope I've given you an overview of this kind of detective story behind this first detection. But where does that leave us in a wider context? Now, I started by saying that the reason for searching for black holes in the first place is to understand how they form, and we can only do that by measuring the distribution of their masses across the population as a whole. So measuring the mass of a single object clearly doesn't give us much insight into the whole population. We have also been only able to look really at a very small field right in the center of our galaxy. So this doesn't tell us a great deal about the mass function of different stellar environments. So really this one discovery is only just the beginning. And what are the prospects for detecting more lensing black holes in the future? Well, it's quite a daunting technical challenge. To detect more microlensing black holes this way, we need to regularly measure the brightnesses of billions of stars distributed right the way across our galaxy. Now here you can see a picture of the Milky Way, and I've shown the area surveyed by Hubble so far is so small that I couldn't even show it as a red square in the center. It's actually, that little red square is exaggerated. And we need to keep monitoring all of those stars for years because of the events last hundreds of days. We also need a large aperture telescope to do this because we need to reach very faint stars that are out at distances of several thousand parsecs. And that's in order to reach as large a survey volume as possible. And unfortunately, there's an inverse trade-off between telescope aperture and field of view. And to make matters worse, this is just to detect the events of progress. Astrometry would require additional work, probably from another facility. Well, there is a telescope facility under construction that should help us to overcome some of these challenges. And let me play the video here. This is drone footage of the Vera C. Rubin Observatory, which is currently under construction at Cerro Puchon in Chile. It will have an effective aperture of 6.6 meters, and that means that it will be able to observe even extremely faint stars. But due to its groundbreaking optical design, it will also have a field of view 3.5 degrees on a side, but a spatial resolution sufficient to distinguish stars even at the very crowded center in the middle of our galaxy. So that field of view is wide enough that it can monitor a huge area of sky every night. This movie shows a simulation of one of the survey strategies that's currently under consideration. The graph on the left shows the map of the whole sky, and the colored dots represent where the telescope will be observing at any given time. And the movie shows a time lapse of just one night of telescope survey operations, showing just how large a survey region it will cover at every time. Now, Rubin Observatory is due to officially start survey operations in April 2024, and it will continue night after night for 10 years. So this survey is ideally designed to discover a wealth of microlensing events right across the entire sky, and we hope many more events that will be candidate galactic black holes. So I hope I've given you a taste of why black holes are such fascinating objects and some insight into our very first detection of an isolated stellar mass black hole. So let me wrap up by saying the future prospects for finding more of these most elusive of objects are looking good as we look towards landmark facilities like Rubin Observatory. This may tell us where these objects can form from and how they can evolve. So with that, I will say thank you very much for listening. And if you have any questions, I'll do my best to answer them.
Great, thank you very much. Mary, you had a few questions. Do you want to start off by asking those?
Yeah, they may not be appropriate. I'm used to microscopes that are different from microlensing scopes. And so my big question is about stability. You know, the stability of the microlensing telescope. And, you know, if there's noise in that position, then how does that affect your results?
So with any observation, of course, there are many varied ways of noise getting into the observation, for sure. In this case, the telescope is really an object in nature in that we're using the gravitational pull of this central object, the lens, to magnify the light from the background star. So we can control the noise in our own measurements, usually by using a larger aperture telescope so that we can gather more light from that background star, which helps us to get a greater precision. Or we can also use facilities with a higher spatial resolution for the positional measurement, which, as I said, usually involves using Hubble and getting above the Earth's atmosphere. So that's one way in which we can control some of the noise sources in our measurement. But although the positional measurement is very small and has to have that very, very high precision spatial resolution, the brightness signature of these events is actually relatively large. And compared with the noise sources in our instruments, we don't actually need that big a telescope in order to overcome those noise sources and get data that's precise enough that we can clearly see the signature.
Okay. The other question that I had to ask, I may not be germane anymore now that you made that an answer, but I was asking what is the wavelength of the source, and what I really meant by that is what wavelength are you studying? And you're telling me it's gravitational pull that you're looking at?
That's right.
And I don't know where that falls on the wavelength spectrum. I'm a chemist, I deal with
Absolutely, absolutely. Well, in fact, we're really lucky in microlensing because the gravity of the source is what's focusing the light towards us. All of the light from the background star is focused in this way. So we can look at any wavelength of light.
So you can look at visible, or you can look at X-rays, or you
Yes.
can look at.
Exactly. And
Okay.
usually the background sources are brightest in the optical spectrum. So we can use relatively straightforward CCD images at optical wavelengths.
All right. Okay. Thank you.
Thank you.
Great. Robert, you have your hand raised?
Oh, yeah, thank you. So I have two questions. One is about the brightness change. How do you know that that's not like a planet moving around the star? And the other question is, I just trying to understand the bigger picture of what you're looking at. You're trying to you're trying to get a distribution of primordial black holes. Is that correct?
Okay, so let me answer the first one first. So can we distinguish the microlensing signature from other kinds of variability, including a planetary signature, for example? And the answer to that is yes. Microlensing is actually quite a distinctive signature. It's microlensing events, because they occur due to completely unrelated objects in the sky. A background source can be doing absolutely nothing, completely blameless life for millions of years, and then a lens passes in front of it and it gradually gets brighter and fainter. And because it hasn't done anything else for such a long period of time, that can be used to rule out other forms of variability, because if there was something intrinsically variable about the source, unrelated to a lens, then it would have done it. We would have seen it in the prior survey data. Now, if the lens has a planet signature going around it, yes, we can see that, because instead of being a nice smooth magnification signature, we see an extra bump in that magnification due to the gravity of the planet, as well as the gravity of the lens itself. So yes, to answer that question, we can distinguish those forms of variability because they give quite different signatures. Now, the second question you asked was about finding primordial black holes. Now, there's a number of different lines of evidence for the different categories of black hole. And primordial black holes have been searched for a wide range of different lines of evidence, including they've looked at the gravitational wave signatures, they've looked at dynamical heating of dwarf galaxies, they've looked at star cluster in different galaxies even. They've not detected primordial black holes. What they've actually managed to do is put limits on where they can possibly exist. And mostly they've managed to rule out that they don't exist in most of these environments. And there is just a relatively small window left of mass range in which, if they form at all, then they can only form within that limited mass range, or we would have seen them through other signatures. And so microlensing can be used to look at the masses of the black holes that we discover, because the distribution of those masses will be quite different if they formed from stars versus if they formed from primordial mechanisms. And so it's that distribution that will tell us the difference. I hope that answered both questions. Thank you.
I have a question, and that's, is there theory about how many stellar black holes there should be?
There is. I don't off the top of my head have a quotable number for you. There's massive stars occur, I think it's roughly sort of 10% of the stars that form are of the very extreme mass end. So we expect that there's a reasonably high percentage of the galactic population should have formed as massive stars, which burn through their nuclear fuel very quickly. And therefore, some of those stars should have formed black holes. So they should be there. It's just that they're so hard to find that we really haven't had the means to do so before now.
And is the thinking that the supermassive black holes at the centers of galaxies, that those were largely primordial black holes originally, or not?
No, some of those, they have to have formed by another mechanism. They cannot have formed by simply being a star and then just accumulating more and more masses, because they appear to have had very large masses at very early stages of the universe. And some of the theories that I have been reading in preparation for this talk, they're talking about direct collapse into massive black holes. They're really looking at very, very dense regions of very high density matter in the center of very, very early time galaxies, and that those could somehow have collapsed directly without necessarily forming stars first. They simply form the black hole directly, but with a very much larger mass. So that's quite a distinct formation mechanism from the stellar black holes that I explore.
Other questions from anyone?
Hi there, I have a question. So I'm curious, when you're looking at these areas of high gravitational pull and high mass, how does the concept of dark matter factor in? As you know, how are you able to identify that this is a black hole as opposed to sort of a quote blob of dark matter that I don't know how the density of that would differ from a black hole. So I'm just curious how you rule that out as a possibility.
Well, microlensing was one of the first techniques that they actually used to look for candidates of dark matter in the Milky Way. And they looked for what were predicted to be called weakly interactive massive particles. And they looked at the distribution of the masses of the objects that we were measuring, of the lenses, and we did not find the excess of mass that was expected. So it appears that that is not one of the explanations for dark matter. So in fact, in the very early days of microlensing, it was certainly a theory that was looked into, and it appears that is not the case. So we're still looking for those characteristics.
Thanks.
Thank you.